All right, let's get started, everyone. Okay, so we are trying a new microphone today. Hopefully the recording will be better. Okay, so last class, so first some announcements. Reminder that we have exam 1 next Wednesday, 10/26 in class at this time. And the exam covers only the portion, the first 8 lectures, right? Lecture 1 to lecture 8, including this, the lecture today. The exam will be closed book and closed notes. You shouldn't really need to memorize anything. It's not going to be that kind of an exam. There will be some objective questions and some problems. You also have access to all the previous exams for the versions that I've taught on EdSTEM. So that should give you an idea. But again, that's just an idea because the content is evolving a little. To give you an idea of the kind of problems to expect. All right. And another important announcement for the exam is that we'll use an extra room for the exam, the one across the hall. So we'll have maybe 75% of the students here and 25% sitting there, so that we have some space for everyone to sit. And any questions about the exam? Okay. And in the discussion sections this Friday, the TS will kind of review the material from the last 8 lectures a little bit and maybe go over some examples so that you can be ready for the exam. Okay. All right. So last class we were talking about one of the biggest ideas in computing, which is the use of non-determinism.
Like that. I do hear the Come on.
Yeah, for people attending on Zoom, I disabled mute upon entry because that was causing problems. So if you're joining as a participant, please mute yourself. Okay, so we saw that the clean star operation of a function computable by a DFA is also computable by NFA. And what we'll do today is kind of look at some other examples of NFAs, kind of try and play with the definition, and then there's going to be a twist in the tail. There's no screen sharing.
There's no screen sharing, and your voice is like duplicated.
Okay. All right. So let's do a brief review. So recall, let's recall what an NFA is. So we have So we said formally an NFA is defined by a transition function, which takes a state that you are in, and one of the usual symbols 0 or 1 plus an epsilon transition kind of symbol, and then tells you a subset of states that you could potentially branch to, right? You could go to any one of these things, and you're also given a set of accepting states, right? So formally, you have to tell me kind of a table. You have a state, 0, 1, epsilon. When you're state 0, you have to tell me what is the subset that you could potentially branch to when you see the symbol 0. What's the subset that you can branch to when I see the symbol 1? What's the subset that I can branch to spontaneously without seeing any symbol? That's the epsilon transition. Okay, and so on and so forth. From state 1, also you have to tell me all of these things. Even for the last state. Okay. Let's do an example to maybe understand this a little better again. Let me call it, maybe N4. So this example is meant to illustrate something about the epsilon transitions. So let's say we have something like this, right? Maybe okay. So this is what our NFA diagram looks like. And what we have here, what makes it an NFA and not a DFA, you have these epsilon transitions, right? So those are the main things that are very different. And suppose I give you input 1. So what is N4 of 1? So what does this NFA output when the input is 1? Well, let's kind of do a simple walkthrough, right? We have the starting state, which is 0. And what happens next? Any guesses? So what did we say about the epsilon transitions, right? No matter where you are, you should spontaneously split and take off all the epsilon transitions, okay? So from here, we should go to the state 1. Right, so you should have a spontaneous split to the state 1, okay? And not only that, but once you split to 1, even 1 should split spontaneously to 3.
What's the purpose of having 2 epsilons? Why not just go straight to 3?
Right, I'm just following this chain of epsilons. Okay, so whenever there's an epsilon transition, I take it without reading any input. So I should just keep doing it recursively. Okay, any questions about this? So this is what we're starting with even before reading any bit. Okay, and now we read the input, which is 1. So from 0, if I read 1, I get to state 2. And from 1, there's no edge label 1, meaning that's a dead state, right? The universe has been cut off. And from 3, you go to state 4. Okay. And of these 2 possible universes, one of them is in accept state, right? So 4 is accepted by the NFA. So N4 of 1 should be 1. Okay. So remember, we only decide what the output of the function is based on the states in the final layer after reading the entire input. You can't decide it earlier. You can't declare victory before you read the entire input. Okay. Any questions about this? Okay, so the key point is that you should follow all of the epsilon transitions and not just the one edge that you see or anything like that. You have to follow the entire chain. Okay. All right. So let's do one more example. I want an NFA which accepts all strings that have a 1 in the last 3 positions. Okay, so I want to accept all strings which have at least one 1 among the last 3 positions. So something like 0, 1, 0, 0 is fine. All zeros followed by 1 is fine. As long as at least one of the positions in the last 3, one of the last 3 bits in our sequence is a 1, we should output 1. Okay, so f of 1, 0, 0, f of 0, 1, 1, maybe f of 1, 0, 1, 0, 0, 1. These should all be 1, whereas f of something like this should be 0. Okay. So let's design an NFA for it. So one of the things to keep in mind is that even, I mean, designing NFAs is, I think, easier than coming up with DFAs. So maybe for this program, you could potentially come up with an NFA, but to keep things simple, let's just try and find an NFA. Okay. So any suggestions on what I should do to identify if there's a 1 in the last 3 bits? Well, you know, so what do we need to do, right? So we have to decide kind of when we start seeing the last 3 bits, right? So we kind of saw this trick earlier as well. So what I can do is, you know, maybe I'll just keep looping in the start state, but then have an epsilon transition at some point. Say, hey, I'm kind of at the position where I have to check the last 3 bits of the string, right? So I'll say you have a 1, you know, maybe you have a 2, maybe you have a 3. Okay, so so what is this saying? You know, somehow you get to decide which of the last 3 bits is going to be a 1, and then you take that epsilon transition, you have to check that is a 1. And what follows afterward, you know, it doesn't matter as long as it's no more than 2 bits long. All right. What should my accept states be here so that I get the language that I get the function that I want?
2, 3, and 4.
2, 3, 4. Okay. So the intuition is that either the 3rd bit from the end is a 1, or the 2nd bit from the end is a 1, or the last bit is a 1. And this epsilon transition helps us branch accordingly, right? It helps us choose which case we are in. And in any of those cases, you will end up at an accepting state. Okay. Any questions about this example? Yeah. So that's just so that, you know, we are kind of looping until we believe we are at the very end. Like we're kind of, you know, the function that we're computing shouldn't really care about what happens in the beginning, right? It only depends on the last 3 bits. So we're kind of ignoring whatever happens until we decide, okay, it's time, you're at the end of the string, let's start checking if you're seeing a 1 or not. Okay, yeah?
semantically, does 2 correspond to the last bit being 1, 3?
Yeah, 2. Yeah, that's a very good interpretation. So kind of, if we end up here, that's as if like saying the last bit in your string is 1. That means we keep, ignoring all of the bits. We just stay at 0 until we are about to read the last bit, when we take the epsilon transition and end up at 2. Okay. So last bit is 1. Second to last bit is 1. Third bit from end is 1. So when we talked about designing DFAs, I said, you should really think like a finite automaton. You have a small amount of memory and you should think what you should memorize and then how you should move along, how you should update this memory, right? For NFAs, there's an added twist, which is you also get to decide when to branch. Okay, so you kind of have to think, okay, what's the important thing? When should I start exploring this option or this branch of the universe? Okay, yeah?
So if we have a string that has like, say we have a like 0, 1, but this can still return even though the rest of the string is less than 0.
Right, so as long as there's a 1 in the last 3 positions. So, from the end, there is a 1 in at least something which is within the last 3 positions, right? Yeah, that makes sense. Yeah. Any other questions? Yeah. Yeah, so that's a good question. Maybe that should be on the exam. But yeah, you might need to modify this construction, right? As we wrote it here, it would accept something like 0, 1, because you just kind of take that branch and it satisfies this assumption that you have at least a 1 in the last 3 positions. But maybe to modify it, you would make this epsilon something else and add some dummy states before. It might require some change. Okay, but that's a good question. Yeah. You could. In fact, this problem, you could even maybe make it a little less complicated. There is a DFA, I think, which has like 4 or 5, some smaller number of states, but you can definitely do it with a DFA as well. But again, doing with a DFA somehow requires a bit more thinking, whereas NFA is kind of easier to do, right? Okay, yeah. So why is the 1? So that's kind of like, this is the 1 that tells us, okay, the function has the string has a 1 in the last 3 bits. So imagine, so let's consider 3 cases, right? Your string has lots of bits, a 1 and 2 other bits. Okay, so this is one class of strings that we have to accept. There is a 1 in the 3rd position from the end. And then you also have a scenario where, maybe this is something else like a 0, and then you have a 1 and something else. Okay. And similarly, maybe you have something like 0, 0 and a 1. Okay, so this is a position. We have to see a 1 in one of the last 3 bits. Okay, so the idea here is we are trying to identify that 1 and jump to an accepting state. Okay. So we keep skipping things until we think we're almost in the last 3 positions. And if you see 1 there, we are in good shape. So we kind of jump to an accepting state. All right. Yeah. Yeah. But, again, so maybe let's do an example to illustrate kind of this counterintuitive nature of NFA computation. So maybe let's say my input is 0, 0, 1, 0, 0. Okay. So what is this? I am not going to draw all possible branches. I'll draw just the relevant branch of the universe. Okay, so this is the diagram for reference. And what's the input we are looking at? 0, 0, 1, 0, 0. So we start with state 0 there. And again, as I said, I'm not going to draw everything. I'm only going to draw the relevant branch. So because there's an epsilon transition, realistically speaking, you should already split here into a 1 and then exploring that branch as well. Okay, but let me draw the branch which makes it output 1. Okay, so if I see 0, one of the branches will say you are at 0, you stay at 0. Okay, I read 0 here. I'm at 0, I stay at 0. Okay, so every time I see a 0, I should be doing a spontaneous split. Maybe let me write it this way. Okay, and then I should do a spontaneous split because of this epsilon transition, right? And I see another 0. I should go to 0 here. And then I should do a spontaneous split. Okay. And I mean, a lot of stuff happens kind of, here, these things kind of die because on 0, there's no edge out of 1. But here, when I see a 1 from state 1, I go to state 2. Okay. And then when I see a 0, I go to state 3. When I see a 0, I go to state 4. Okay, so there are other branches, that happen here, which I'm not drawing, but at least in one of these branches, I'm ending up after reading the entire input at an accepting state 4. Okay, so this implies that n phi of 0, 0, 1, 0, 0 is actually 1. Okay, any other questions about it? All right, so that's kind of another example. Now let me tell you, let me give you another example of the power of NFS. And this goes back to a question that I asked in the last lecture, right? Recall and if we had a function f, I also define the reverse of the function. Okay, so you can write f reverse of x is just the original function applied with the string x reversed. So the last bit becomes the first bit, the last but 1 becomes the second bit, and so on. So you reverse the string and then you apply the function. Okay, and I ask a question. If f is computable by a DFA, what about the reverse of the function? Okay. Intuitively, it seems very counterintuitive that you can do anything with f reverse, right? Because a DFA by definition has small memory and it has to see the input from left to right. Okay, it can't remember what was the first bit or many bits long in the future, right? Whereas when you talk about f reverse, you're not giving it in the right order. How is it going to correct it? Okay, so what should you, what do you think? So I'm going to, let me spoil the suspense by saying there is an NFA at least for F reverse. And the question is, how do we design an NFA for F reverse, given that there is a DFA for the function F? Okay, so, suppose we have a DFA D for F. Okay, we have some start state and all kinds of other states. Maybe this is 0 going here. This is state 1. This is 0 going to state 2. And maybe the 1 is going back. Maybe this is state 10. 0 to state 13. 1 somewhere else. And maybe this 0 goes here, maybe this 1 goes here, and so on. Okay, so we have some DFA with some accept states, maybe they are over here. Okay, and the accept states might also have edges, right? It's just some random diagram. It doesn't matter what that is. So this is a DFA, which is computing the function F. But now we have to check or compute F reverse with the NFA. So any ideas on what we could potentially do? Yeah?
Use that same 0, 1 loop with an F1 transition, and then feed that output.
You mean like from this, so from the accept states?
Or no, into the initial state of the DFA.
So here, so how do I add arrows? So remember, we're seeing the entire input in reverse.
Well, I just noticed that for our N5 example, when we used like between state 0 and 1, it seemed to reverse the string since the output.
Yes, but maybe that's specific to that example. So let's think of the kind of random diagram without any structure, right? Yeah?
Maybe like create a start state that has an F1. I guess.
I think you're almost there.
And then like track the transition, whichever one.
Yeah, so it's basically like, what would you do if I ask you to walk backwards, right? So let's do that. So the modification, okay, so the suggested idea is follow the edges backward. Okay, so we're going to reverse the entire order of computation. Okay, so instead of going from A to B, like some of you are saying, you have to go from B to A. Right? And I'm going to do it explicitly for this diagram, even a little bit messy, but I think it's not too bad. Okay, so this is the original DFA. Now I'm going to overlay the new NFA on top with these blue edges. Okay, so first, for my string, for my original string to be accepted, I should end at an accept state. So if I had to walk backwards, where should I start from? From an accept state. But there are multiple accept states. So what's the fix for that? Yeah? Exactly, right? So I'm going to first create a new start state. Okay, and then create epsilon transitions to all the previous or real accepting states. Okay, and these will no longer be, okay, so maybe, so we have this, and now what I suggest I'm just going to flip the direction of every arrow.
What?
Okay, in some sense, for X reverse to be at an accepting state,
God,
I should
so what
end
class?
here.
From one of my
Right.
econ ones. Like,
So the
about
first
starts.
bit I read
I got like
should
15
be
kids who, like,
The
something that
retards.
leads into me.
who got in like
Okay.
the three like.
So if I came here, where should I have
the
come
whole
from? I
class is like
should have
all
come
my
from
clerk,
2.
like,
So my
Mhm.
first bit
and then
should
all,
take
like,
me to
and
Mm-hmm.
then there's just three random kids who are like in it and no one knows.
Fuck.
And I got those guys. And this last guy's paragraphs that he wrote is
Keaton,
just
mute your
retarded.
mic.
incoherent.
Oh
And
god.
I'm
And the same here.
I basically said like this is fucking cool.
Keaton, mute your mic.
And he like
So I followed a sequence of bits from the starting state and end up there. That's the usual definition. But now I want to know if I flip the string, I would end up start from there and end here, right? So we're just kind of tracking, okay, if I did that, then I should have come here. If I did that, then I should have come there, and so on and so forth, right? So I just reverse all the arrows. Okay, and what should the new accepting state be? Any guesses? Like, now I define the program, I have this start state, I have a bunch of arrows, and what should the new accepting state be? Well, yeah. Yes. Exactly. Right. So you can imagine it's like a puzzle, right? I tell you, okay, the way to go from here to, maybe let's say the village theater is you go out, you take a left, you go a right, you take a left, you go a right, and so on, right? Now I ask you, okay, you ended up at the village theater. What sequence of instructions did you follow in reverse? You just flip the order that I gave you. Okay, that's exactly what we're doing, just flipping all of the directions. All right. So in words, the construction is add a new start state add epsilon transitions to all the previous accepting states, reverse the direction of all arrows. Make old start state the new accept state. Okay, we are back online. Okay, hope we are back online. All right. So for instance, if you focus on, okay, here, let's see, like 2. Right, so this was a DFA, so there was no violation in terms of having a single outgoing edge for each label, but there are 2 edges marked 0 coming into this state. Okay, when I flip the arrows, what happens? I have 2 outgoing edges with the label 0, right? So even if my original thing had a DFA and a single accept state, I would end up with an NFA. Okay. Right. So this shows us that at the very least, F reverse is computable by a NFA. Okay. Any questions about this construction? Again, like, this is kind of a way to just illustrate. It's not a very useful operation. I don't think it's as useful as the concatenation or clean star, but this is just a way to illustrate this sort of non-intuitive power of NFA, right? So NFA, as we said, they have to read the input from left to right, but still they're doing something with small memory backwards. Okay. Any questions? Okay, all right. So let me now state something which should be somewhat confusing, or at the very least mind-boggling. So one of the main things that we'll prove is the following. So far, we've been looking at NFS as way more powerful objects, right? They could do concatenation very easily. They could do all this multiple branching. They could exploit it. They could do reverse. They could do clean star, and many of these things, right? So you can wonder, what's the limit to their power? How much more powerful are they than our plain and simple DFAs, which only get to hop into one branch each time, okay, without any multiverse? As it turns out, not very much. So every NFA has an equivalent DFA. Okay. So in particular, we will show this mind-blowing fact that for every NFA, if I gave you an NFA n, no matter what it is, there exists a DFA. There exists a DFA with the same functionality. Okay. So far, no matter what NFA you give me, there is still a DFA which will be just as powerful, which computes the exact same function. Right? Again, this is very, very counterintuitive, right? When you think about it, NFS seem to have so much more power. They were doing this multiverse branching. They only needed to accept in any one of those branches, but DFS are very deterministic. Okay. So before we prove this theorem, let us kind of just revisit some corollaries of it and what we saw, right? suppose I have two functions, f1 and f2. Are computable by DFAs. Given this theorem, what can you say about the concatenation? The concatenation also has a DFA for it, right? Because we already saw that if you start with two DFAs, the concatenation can be computed by an NFA. And this theorem kind of allows us to go back into the world of DFA, right? So we go from a DFA, two DFAs, the concatenation is an NFA. And now we have this hammer which says, okay, you can retrace your steps and rebuild a DFA for the NFA that you have, okay? Then is computable by a DFA. Okay, so how would you prove it? You'd say, we already saw that f1 cat f2 is computable by a NFA. Theorem says we can magically build a DFA for this NFA. Okay, so in some sense, we are using the NFA as a go-between to go from to compute the concatenation operation. All right. At the end of the day, we don't see it, but I have two DFAs. The way I get to a new DFA is first build the NFA and then use the theorem. Okay. And you get similar corollaries, right? And if I have a function that is computed by a DFA, then their star, the clean star of the function, is also computable by a DFA. Okay. So a couple of lectures ago, we said, okay, DFAs are closed kind of under this and or not operations, right? If some things are computable by DFAs, you can put ands together and will still be computable. Now, what we're saying is not only is it true for ands and nots, but also for concatenation, for a clean star, for the reverse operation, and many other things. And the way we are doing that is via this powerful hammer, which should be kind of very counterintuitive, that every NFA has an equivalent DFA. Okay, any questions about the statement of the theorem and its implications? Yeah?
Does this relate to P equals NP?
Not really. So it relates to it in the sense that, as you'll see, this idea kind of plays a role in there. It relates to saying that NP is within X. So if you allow me non-determinism, allowing non-determinism is kind of the same as allowing me, can be simulated with an exponential increase in time. Okay, so that's what it means there. But in the context of NFAs and DFAs, you have additional constraints that it has to be single pass, constant space. So it's trickier. Okay, but it's kind of a beautiful theorem, right? You have this powerful abstraction that we built in between, but then we realized that you don't even need it. It's just giving you the same power as DFS. So you might ask, why do this in the first place? We'll talk about that a little bit as well. Okay. All right. So let's take a 5-minute break. And when we come back, we'll talk about how to prove this theorem. And let me say, I'll also tell you why NFAs are still important, even if they're equivalent to DFAs. Okay. So I forgot to say, today's office hours, my office hours are moved to 4:30 to 5:30 instead of 2 to 3. So I have something else from 2 to 3, so I'll be from 4:30 to 5:30. Okay, so let's get back. Oh, all right, we're back. Okay, so let's say we have an NFA which looks like this. Right, you have a start state, and maybe when you see bit 0, you go to something like this, maybe. Okay, and maybe when you see, like, let's say you have 2, 4, maybe 6. Okay, and when you see 1, you go here, go here. Again, this is kind of a toy example for us to play with. It's not meant to capture everything, right? So, this is just a picture, and let's see what happens if there are many other transitions which I'm not even drawing. Let's say this is our NFA, and what happens if my input is just 0, 1, and something. Okay, so what happens is, well, you start at the start state, and when you see 0, you have to branch. You create 3 branches. Okay, just so that you don't get the wrong idea, let me also put the 1 edges. Okay, you see 0, you take these branches. Now you see 1, what happens? Well, you get 2 and 4. You get 2 and 6. You get 4 and 6, right? This is how we defined, this is our definition of NFS, right? Every time you see a bit, and if there are branches to take, you create a new branch of the multiverse and explore that. Okay. So if we have to capture this entire computation with a DFA, let's ask ourselves, what do we need to do? Okay. And remember, there's a lot of stuff going on afterward, and then at the very end, you read the entire input, and then you have a bunch of universes. You check if any one of them is in a accepting state, and then you declare victory. Okay. So imagine you're trying to simulate this entire thing with a DFA, right? The first problem is that the number of branches is exploding. Okay. But a DFA cannot remember this. It only has access to constant memory. So what can we use as leverage to get around that? Yeah? Exactly, right? So it kind of, I chose this example with that in mind, right? If you have two branches of the universe, which are exactly in the same state, for future computation, we don't need to simulate them both in parallel. Okay. It's as if, I mean, we know that both of them are going to behave exactly the same afterward. So why simulate both? We can kind of merge or even get rid of some of these branches as long as we have at least one copy. Okay. So concretely, like let's say you have two copies of 2 here, right? You have 2 copies of 4. You have 2 copies of 6. Nothing would change if I, maybe somehow like, dropped off this branch, and this branch. Okay. So the main thing that I need to know to carry the computation forward is what states are actually reached across all of these universes. It doesn't matter how many copies of the universe are in state 6. As long as there is at least one, that's the only thing that I need to track. Even if there are a million copies of 6, I only need to track one of them, because what comes afterward is completely determined by what state you're in. It might branch, but the state determines the tree afterward. Okay. Is the intuition clear? Right? So same thing here. Like, I only need to track which states are we reaching and so on and so forth. Okay. So let me write that as the punchline. And that's kind of the core of the argument. Two copies of same state at same level. That's important. Can be collapsed. Let me put collapsed in quotes into one. Okay, by collapse, it just means you only need to keep track of one of these branches. It doesn't matter how many times you see it, as long as there is one, I just need to keep track of which states are alive at this state of the input. Right? So when we read the input, we kind of go in these phases, right? So here you're only in state 0. Here you're in 3 possible states. The universes are split into 3 kinds, 1, 3, 5. Here, all the universes are only split into 3 kinds again, 2, 4, 6, and so forth. So I only need to keep track of which universes are realizable. That's it. Okay. So that's the main idea. for each level, we need to know. By each level, I mean, like, what happened after reading 10 bits of the input? What happened after reading 11 bits of the input? What happened after reading 20 bits of the input? I just need to know what states are reachable at that level. The number of copies is redundant information that we don't care. Okay? Any questions about this intuition? So if I just know this, I can carry the simulation forward and at least get the same conclusion as what my NSA would. All right? So to make the matter simpler, and as a first cut, let us suppose that, let's assume the NFA has no epsilon transitions. Okay, so we'll see how to fix when, fix the construction when there are epsilon transitions. But, for simplicity, let's start with a case where the NFA has no epsilon transitions, but you still might be branching, right? Because maybe there are two edges going out of a node with the label 1. Okay. And to formalize, we are given what's our goal? Given a NFA, N described as a transition function in a set of accepting states, and we have no epsilon transitions in here. And let me say this is Pn, Sn to denote these are the transitions function and the state, accepting states of the NFA on C states. Our goal is find a DFA D, which has some other transition function, some other set of accepting states, such that D of x equals N of x for all inputs. Yeah, so no matter what the input is, we need to be giving the same output. All right. And if you go back here, what are we having to keep track of to carry the simulation? I had and think, what information do I need to remember to carry the computation forward? The set of states that are reachable. So what should the states of the new DFA correspond to? Any guesses? Yeah? Exactly, right? So if NFA was on states you had an NFA which had states, C possible states. The new DFA D has states, the one we'll decide. We will construct a DFA D whose states correspond to subsets. Right, and which is power set. Okay, so I have to keep track of all possible states that my universes have reached. So I'm just going to create a dummy state for every one of those subsets. Okay, so for instance, if C was 4, maybe okay, 4 is too ambitious. C was 3, the new states of the DFA will be the empty set, which is also a subset. You'll also have the set 0, the set 1, the set just containing 2, 0, 1, 1, 2, 0, 2, and 0, 1, 2. Okay. So if your NFA had 3 states, then we'll create a DFA with 8 states, each one corresponding to a subset of your states of the NFA. Okay. So the number of states in our new DFA will be 2 to the C, right? So we are going to increase the number of states exponentially, but remember, an NFA still had a constant number of states, so the DFA will also have a constant number of states, albeit with a bigger constant. Okay? So we have to now define this new DFA. So we have to specify what is the transition function, what is the starting state, and what are the accepting states of the new DFA. All we did so far is kind of get an idea of what the states of the DFA should correspond to. Okay. So we had to come up with a transition function which takes subsets of states, the power set, a bit, and outputs a new potential state. Okay. So in this convention, technically when we define DFAs, we said the states should be numbers, right? They're just numbers from 0, 1 through whatever 100 or 99 or something like that, right? But I'm going to indicate states by subsets. The names that you give to specific states is not important, just as the variable names you use in a program is not important, but it makes the picture clear. Okay. Any questions? All right. So now we have to decide what should this transition function be, right? So let's go back to our example and see what happens. Okay. So how should we construct this transition function? Well, let's think of the intuition, right? So what are we doing? Why are we doing this subsets as our states? We want to keep track of how the set of reached states in a level curve change, right? So for instance, initially you were at this level. Maybe let me draw level to level. So here, the set of states reached was 1, 3, 5. Here, the set of states reached was 2, 4, 6. Here, the set of states reached was just the state 0. Okay. So however you define this TD, we want, like, if I'm here and I see a bit 0, it should go to 1, 3, 5, right? Because in the original NFA, when you started from there, you saw a bit 0. The next level, these new states appear. Okay, there were 3 branches of the universe, and each one of these was reachable. Okay, and something similar here, right? So you want to keep track of the set of reachable states as they are in our NFA. Okay, so this gives us an idea of what this transition function should do. You're at a level, you have a state. If your NFA branches out, somehow all of these branches should be included for your DFS transition function, because we need to keep track of all the reachable things. Okay, so on, like, maybe if you read some other input, the set should evolve accordingly and so forth. Okay, so how do I define this transition function? I have some subset. Maybe I see a bit A. What should this be? Any guesses? Yeah.
Can we just trace all the transitions of either 0 or 1 and just find out what subset that belongs to?
Why 0 or 1? Because we want to define the transition for each bit. So there's a distinction between the states in I and the bit that we see.
So we would trace it for just that bit.
Just that bit, yes. Yeah. Exactly, right? So again, think as a simulator, right? You have a bunch of things that you reached here. You see a new bit, you're branching out into new universes. I can collapse or aggregate these new universes by only keeping 1 copy of each of these universes. So let's just do that, okay? So the definition, the first cut is going to be, maybe let me write it in words. For each element in I, compute, look at the new set of states that you would reach if you branched according to the original NFA, and then you have to group all of them together, but you only keep 1 copy of each one. Okay, group all of them together and keep only 1 copy. So what's the mathematical operation that corresponds to aggregating sets and keeping only 1 copy? Union, right? So that's exactly what we're going to do. So for every index I, for every state that we are potentially in, I'm going to compute the new set of states that I might end up in and take the union of all of those things. Yeah?
You have to think of it as level by level or just the whole thing.
So we think of it level by level for intuition, but the transition function is just defined for any set. Okay, so the transition function is kind of a one-shot definition. You define it once and then you just let it evolve. But for intuition, I'm kind of drawing it level by level. Like, what do we want to achieve with this transition function? We definitely want to make sure that we do not miss a new branch of the universe if it evolves. Okay, as long as we keep at least 1 copy, we are fine. Okay, yeah.
The I is the subset of the power sets.
I is an element of the power set. Like, I is a subset of the set.
Oh, yeah.
Okay. And just to make clear, this is union of all were all elements in I. Okay. Any questions? So for example, suppose I was the set, maybe 4, 10, 13. Okay. Then TD of I comma 0 would be the union of whatever your NFA asks you to do on the bit 0 from state 4 with the union with 10 and the union with 13. Okay. Any questions? All right. Again, we're just kind of really simulating it as we would in our minds. Right. We just need to keep track of the states that are reachable. So that's exactly what we're doing. All right. So we have the definition of the transition function now completely specified. All right. But to describe my DFA, I also need to tell you what the new set of accepting states will be. Okay, we kind of solved half the puzzle. We kind of figured out how to construct the transition function from the old transition function. And now let's go back to and ask, what should the accepting states of DB? Okay. Any guesses? Yeah. Exactly. Right. So if you go back to this picture, when does the NFA accept? It accepts as long as any of the states that you have in your last level is an accepting state. Okay. Maybe, if your NFA had accepting state 0, 1, 2, as long as one of them occurs here, you would accept. Okay. So if you keep track of this entire evolution and you just write down, okay, here are the states that you reached in the end. As long as any one of them is an accepting state, you should accept, right? So the idea is to really make it exactly that. Look at all subsets of states, and as long as they contain at least one of the original accepting states, it should be an accepting state for the new DFA. Okay. As long as the intersection with the original accepting states is not empty, we are fine. So meaning contains at least one of the original accepting states of N. Okay, so for example, if C is 0, 1, 2, we have 3 states, and suppose Sn was just 2. Okay, so the NFA, whatever you had, it had only one accepting state, which is 2. Then the accepting states for the new DFA would be all subsets which contain the element 2. Okay, so you would have 2 in here, you would have 0, 2, you You'd have 1, 2. You would also have 0, 1, 2. Okay. So even though the original NFA only had a single accepting state, the new DFA that we construct will have 4 accepting states. Okay. Any questions about this? We're really breaking it up into pieces and doing each piece separately. All right. And well, let's also, the third piece of the puzzle would be what should the start state of DB? Okay. So usually, we say like the number 0 is the start state, but here we said we are going to name the states according to subsets. So let's be more specific. So what should the start state of the new DFA be? Any guesses? It should be a set. What set should you start with? Not the empty set, but if you go back to this diagram, so what state are you in at level? Right? At level 0, you're starting at set 0. Okay. So, I mean, it's basically the same starting state, but it's really the set that contains 0. Okay, does it make sense? Okay, so let me summarize. So we had a NFA and with transition function Tn, accepting states Sn on C states. Now we build a DFA TD on the power set. And the formula was TD of I comma A was the union of all possible branches that your NFA could lead you to. The set of new accepting states is all subsets which contain at least one of the original accepting states. Start state of D is the set 0. Okay, yeah.
Do we have to assume no epsilon transitions happen?
So far we did. This is just for first cut, but we'll address the question of epsilon transitions in a second. Okay. Any questions about this? As long as there are no epsilon transitions, everything works out perfectly, right? The entire simulation just doesn't lose even a single bit, right? Every level of the NFA is simulated exactly by the DFA. We don't have to do multiple counts. We just kind of keep one copy for each one and proceed accordingly. Okay. Any questions about this? So if there are no epsilon transitions, then this would work. Yeah.
So the only difference in the start state is that now we're considering even like single states as its own set.
Yeah, because just kind of this nomenclature, right? Because it's defined on power sets.
So because it's defined on sets only, we consider
Exactly. Yeah. It will change a little bit once we go to epsilon transitions, but right now it's mostly for consistency. Okay. Any other questions? All right. Okay. So far, so good. But now, and by construction, for any x you would have n of x equals d of x. Okay, so we did the construction with exact simulation, so you would have this property. All right, but all of this worked as long as there were no epsilon transitions. All right, what if, how do we handle epsilon transitions? What if we had epsilon transitions? Any suggestions? Yeah. Exactly, right? That's a great idea. So let's try and do that. But let me build up to it with a simple example. Maybe suppose, it's an example, and this is what our NFA looked like. We kind of saw something similar earlier, but let me write it anyway. Okay, so this is what our NFA looked like. And yeah, maybe I'll do something else as well. Okay. So this is our NFA, and let's say our input X was just 1 and 1. So we start with 0, the start state, but we immediately have to branch, right? There is a spontaneous split. Okay, this is a spontaneous split because there's an epsilon transition out. Now you read your input bit 1. 6 has nothing, so it kind of gets cut off. You end up at 2. All right. And then what happens? Well, 2 itself does a spontaneous split to 3. It also does a spontaneous split to 4. And that's where you end up at. And now you have state 1. You read bit 1, you end up at 5. Okay. So I'm just writing down how the NFA is computing, right? How are the states of the NFA evolving in all of these multiple branches? We don't have much parallel branching here, but we have this spontaneous epsilon branching in this example, because that's what I want to illustrate. Okay. And what did we say, right? To simulate the NFA, we need to keep track of all the states at a level. Meaning, here I need to keep track that, you're at 0, 6. Here you are at 2, 3, 4. Here you are at 5. Okay. So we need our transitions to kind of also add these guys. All right. So when you are at state 0, 6 and you read bit 1, you should jump to 2, 3, 4 and not just to 2. Okay. That was the suggestion. So let's try and make it formal. So to make it formal, we need one more definition. And that is the following. For a state, suppose I have some state I in 0, 1 through c minus 1. I'm going to define the epsilon closure, or the set of states which are reachable from S with only epsilon transitions. Okay, so there are a bunch of states which I can reach with only epsilon transitions, right? All states reachable by only by taking epsilon edges plus the state itself. Okay, you always have a copy of yourself anyway. Yeah. Oh, sorry. Thanks. This should be I. Okay. So you just kind of chain all the epsilon things, look at all the possible states that you would reach. You also include yourself, and that's what your epsilon closure is. So for example, if you go here, the epsilon closure, not ESP, but epsilon of 0 would be 0,6. Epsilon of 2 would be 2, 3, 4. Epsilon of 3 would be 3 and 4. Epsilon of 4 would be just 4 itself. There are no epsilon edges out of it, so it would just be the state itself and nothing else. Okay. And if I have a set of states, I can also define something similar. It's basically all possible states you could reach by starting from anywhere in I and only following epsilon transitions, right? It's as if you are in here and I tell you you are allowed to take epsilon transitions. What part of the universe are you going to reach? Okay, what branches are realizable under this setting? So this would just be, you look at all the elements of your subset and take the union of their epsilon closures. Okay. Any questions about this definition? Yeah.
Reachable only doesn't mean only reachable, right? Like, if there was another transition that on top of the epsilon one, it would still be reachable.
Oh, okay. Oh, thanks. It's reachable by taking epsilon edges. Yeah. Good point. Any other questions? Okay. So going back to this example, if I had epsilon of 0,2, this would be 0, 2, 3, 4, 6. Okay, because I have to take the union of these two things. All right. And keep in mind that it always includes the state itself. All right. Any questions? Okay. So now I think we're almost done. So I have a new definition for what the TD should be. So the final DFA D if N has epsilon transitions, can say TD of I comma A. What should this be? As suggested, you should take your usual jumps, but then trace out all the epsilon edges afterward, right? Which is exactly what happens in this NFA definition, right? You are here, you see the state, you see the bit 1, you go to state 2, but then you jump off to 2, 3, 4, right? So you take the same thing as we had before. This was our old definition that we had when there were no epsilon transitions. Now we have epsilon transitions, so we just take the closure. Okay. So that's it. So the main change is this epsilon on top of what we were doing before. Okay. Yeah.
You apply the same logic to a start state.
Excellent point. I was going to get to that. So this kind of almost does it for us, but we still have to ask, what should the new start state be? And as was pointed out, we should apply the same logic to the start state as well, right? Again, recall, we want to keep track of all the possible states reachable at a level, okay? And if you have epsilon transitions, even without doing anything, you're starting with two possible universes, one in state 0, one in state 6, okay? So the new start state should be the set of states that you would reach just from, with epsilon transitions from the original start state. Okay, without doing anything, maybe you're branching off horizontally, even at the beginning. Every one of those is a potential start state for the NFA. So let's put them all together. Okay. And the accepting states remain the same. So the accepting states, they don't need to change from what we did when there were no transitions. Okay, so that's the entire definition. All right. So if you follow this construction, then we are exactly mimicking the behavior of the NFA word for word or state to state, except maybe the NFA has multiple branches with the same state. Doesn't matter. We keep at least one copy. So the entire construction would work. Yeah. Yeah, for sure. Like, think of it as a translation, right? I give you an NFA, I'm giving you a DFA. So you need to know what the NFA is. Oh, no, not the input string, right? This whole thing is defined only in terms of the NFA. You're not allowed to look at the input string before you define the DFA. Okay. In fact, okay. Any other questions? Okay. So what did we conclude? Summary. Now we get our theorem. Every NFA has a DFA. Has an equivalent DFA. Okay. I mean, I find this very mind-blowing. The first time I saw it, I was quite amazed. And when you think of this construction, now it makes much more sense to not think about DFAs. Like from now on, if someone asks you to design a DFA, you can always say, okay, I'll first come up with an NFA, and then I'll come up with a DFA for the problem later on. I know there exists one. I don't have to write it down explicitly. Okay. Let me say a couple of remarks. One, to compute by a DFA, what this says is that it suffices to compute by an NFA. Okay. And another thing is, if you look at this construction, if DFA had, if NFA had C states, then the DFA has 2 to the C states. Okay, so there's an exponential increase in these states, right? And you might ask, like, this construction seems a little bit bloated, right? You're keeping track of all possible subsets. You're doing everything like, in a brute force manner. Is it possible to do something better than this exponential blow up? This is something we're not going to do in this class, but this is almost typed. Okay, so there are NFAs on C states whose computation by DFAs needs 2 to the C minus 1 states. Okay, so there is a DFA on 10 states, which if you, okay, so on 11 states, which if you were to write an equivalent, sorry, if there is an NFA on 11 states, for which the smallest equivalent DFA has 1024 states. Okay, so the construction that we saw, even though it seems like almost brute force, it is kind of close to tight up to this factor of 2. All right. And thinking of NFAs, we'll talk about why it's more efficient and other uses of it in the next lecture. All right. So let me end there. In the next lecture, we'll do an example of this translation and see some other applications.